In 2011, the Government Construction Strategy, or GCS, was first published. This called for members of the construction industry, and publicly funded clients in particular, to become more efficient in the way they deliver work and operate public infrastructure. To meet this brief, the industry needed to change. One of the key problems identified in the GCS was the use of information and data throughout the asset lifecycle. Problem 1 was that teams worked in silos to plan, design, build and operate assets. They collect data and information in different ways, with no common rules about how it should all be managed. This meant that the transfer of data and information was disjointed and often incomplete. As a result, at each stage handover, some of the knowledge that was gained about the asset and the environment for which it functions would be lost, and the incoming team would have to spend time and money to rediscover it. Problem 2 was that teams were not making best use of digital tools to deliver their works as efficiently as possible. The industry had largely moved from the paper-based drawing world to computer-aided design, or CAD. But in doing so, they simply replicated their 2D paper drawings in a digital format. To solve these problems, the GCS mandated that all publicly funded projects must be delivered in accordance with the principles of Building Information Modelling, or BIM. The purpose of this is twofold. Firstly, it puts in place a universal structure and standard process for managing data and information. This means that data and information is collected in the same way throughout the asset lifecycle, which facilitates collaboration by making everyone use data and information in a consistent way. It also improves the handover from the project phase through to operation. In this way, the team working on each stage can easily pick up the work done by the previous one, so they can immediately start building on what was done before. Secondly, it pushes the industry to adopt new technology to deliver work more efficiently. This includes things like 3D modelling throughout the asset lifecycle, so an asset can be virtually built and operated and potential problems discovered and solved before a spade gets put in the ground. And linked models and data sets, so that cross-disciplinary teams can better collaborate, using the same data and information. The Environment Agency is a major operator of assets and client to the construction industry. So we stand to make big savings and deliver better outcomes across all of our activities by adopting BIM. In these e-learning modules, you'll learn about the theory behind BIM and how to apply this to EA projects and assets. Welcome to the first module of the Environment Agency's BIM e-learning. In this module, we will look at the basic principles of information and data, and introduce the principles and purpose of BIM. In this e-learning module, you will learn the key concepts you need to know about BIM. To start with, we'll look at some general concepts about information and data. You will learn the definition of data, information and knowledge, the difference between different types of file format and why it's important, about verification and validation and why they're beneficial. You'll learn about metadata, how it's applied in the EA, and how it's used to classify data and information. And you'll learn about different kinds of models. After that, we'll talk about the key principles of BIM and how it's relevant in the Environment Agency. You'll learn the aim and purpose of BIM, the measures of BIM maturity or adoption, about level of definition, a key BIM concept, how to define and use a volume and location strategy, and the use of COBie to exchange data and information. Data, information and knowledge sound like they mean the same sort of thing, but in computing, they have well-defined meanings. In BIM, we talk a lot about data, information and knowledge. In fact, the I in BIM means information. So before we tell you about the nitty-gritty of BIM, let's have a look at some basic principles. Data means items that are presented without context. These items can be numbers, words, texts, sounds, images, anything that a computer is able to store. Here is an example of some data. You can tell that it's a load of numbers, but you don't know what they mean because there's no context. Information is items which are presented in context. For example, here are the data from the previous example. These are the same numbers as before, but this time We've put them in a table and told you what they mean by adding headings. We've turned the data into information. Computers are great at doing this. We use things like spreadsheets all the time to process data into usable information and present it in many different ways. Knowledge is the ability to take information and to use it. It's being able to make judgments, form opinions, and create predictions. For example, here's the information that we looked at on the previous page. You've probably figured out that this is a hydrograph, a plot of the flow rate of water at a particular location over time. If you give this information to a hydraulic modeler, along with other kinds of information like surveys, maps, and so on, they could use their knowledge to predict where a flood would happen. Computers store data and information in files. Different types of applications do different things with data and information. For example, Microsoft Word is mostly about, well, words, whereas AutoCAD is about drawings. For this reason, applications use files with different formats. A file format is just a way of storing data so that an application can use it. Think of a file format as a type of language. Word speaks in DocX and AutoCAD speaks in DWG. It's fine that they don't speak the same language, because they do different jobs. The apps need different file formats to contain the different types of data and information that they deal with. There are two main types of file format: native formats and open formats. A native format is the default format that a particular app uses for its file. For example, just as a French person has French as their native language, AutoCAD has DWG as its native format. Native formats are often proprietary. That means they're made by the people who made the app, just to work with that app, and they don't tell anyone else how to use the format. This can be a good thing. The developers can include new advanced features in their app, then update the file format to suit, and they don't need to worry about what other developers are doing. The downside is that you need that app in order to open or change the file. This could get expensive. For example, imagine if all our supply chain used different CAD packages to produce their drawings. We'd need to buy licenses for all those pieces of software in order to work with our supply chain, and we'd all need to learn how to use an array of different software packages. That's why we also have open formats. These are typically created by groups or committees who agree on how the format should work. They publish details about the format so anyone can develop their app to use it. Because many apps can use open formats, that makes them much more portable than native formats. That makes life easier for us, because if we just use one app that's able to read the open format, it doesn't matter what app our suppliers use, as long as they send us the files in an open format. However, because open formats are developed by committee, they don't always support new features implemented by specific apps, and it can take time for the format to be updated to support these. One of the goals of BIM is to ensure that we can trust the information and data that we receive. There's no point in us storing things that are of poor quality, or in a form that we can't use. To achieve this, BIM introduces the concepts of verification and validation. Verification is a tool for checking the accuracy of data. It checks data against a defined set of rules, to check that it's reasonable. In other words, verification is checking that the product basically looks right. Because you're checking against a rule set, verification can often be carried out automatically by a computer. For example, imagine you ask one of your colleagues to email you the phone number for a supplier. When you read the email, you notice what they've sent as a phone number is actually a word. You know that a phone number should be a string of numbers, 10 digits long. The data you've received doesn't match those rules, so it is not verified. Validation is about checking that the product you receive does whatever it is you want it to do, that it meets the need. Validation isn't about matching rules, so it's harder to automate. A product can pass verification but fail validation. Just because it is in the format you're expecting, it doesn't mean that the data or information is correct. For example, imagine your colleague sends you the email again, and this time they send you something that does look like a phone number. It passes verification. But how do you know it's the right phone number? One way would be to call the number and see who answers. If the supplier you're expecting answers the phone, then you've validated that the number is correct. When we want to build a new asset, maybe a collection of flood walls or a new pumping station, we only get one chance to build it and get it right. It's impractical to build a prototype somewhere to test the product and make sure it works properly. To do that, we have to build a model. A model is a representation of something. In this case, it could be a physical model built to scale, or it could be a virtual model built on a computer in 3D. Either way, it's something that lets us examine the performance and operation of the final product without actually building the product. The concept of metadata is a simple one and an important one for BIM. Metadata is data which describes other data. What does that mean? Well, think of something like a book. A book contains data. Hopefully, quite interesting data. Otherwise, it's not a very good book. Well, there's also bits of data that describe the book. These are attributes such as the title of the book, the author, the type of genre, when it was published, the price of the book, all things that describe what the book is, and which help us to classify it. Metadata is really useful for helping us to tell things apart from one another, or for finding a particular piece of information in something containing lots of information. You use metadata all the time, probably without noticing. For example, if you wanted to buy a particular book from a website, you somehow need to find the book on the website. Now, the seller could just show you a list of all the items they sell and let you pick the one you want. But this could take you quite a long time. So instead, you probably use the search function by typing in something meaningful to search for the book you want to buy. When you use a website in this way, what's happening is the text you've typed into the search box is being matched against metadata about objects in the shop. You use the metadata to quickly refine a large amount of data. BIM enables us to use metadata in the same way to describe our assets. For each of our assets, there's lots of different types of metadata we're interested in. By making sure we collect this metadata and doing so in a structured way, we make it easier for ourselves to find things about our assets later on. One of the things that metadata allows us to do is to place our data in various classes, defined by the needs of the organisation. For example, if we refer back to our online store, each product for sale is a data item. This list on its own isn't very useful, so they're also stored into different classes. The type of product it is, the format, the author, and probably many more. This data classification makes it easier to use the dataset. For example, to identify all the books we sell or all the music from a particular artist. In the Environment Agency, we classify our asset register in exactly the same way. For example, we classify our assets on attributes such as type, is it an embankment, pumping station, flood wall, and so on. Location, where in the world is this asset? The sort of maintenance activities we carry out. Who owns the asset? Is it the Environment Agency or some other party that's responsible for the asset? Classifying our data lets us quickly answer questions about our assets. For example, if we decide that a particular type of maintenance activity can't be carried out, we can use the classification to quickly identify which assets will be affected. We know we can use metadata to classify our assets. But how do we know what the classes are? And what properties or attributes belong to each class? For that, we need an information model. An information model defines the rules and relationships between our different classes of data. For example, at the top level of our classification, we could have the purpose of the asset. This is our top level class, and it groups all the assets that work together to achieve the same goal. Beneath purpose, our next level could be the type of asset, and you might even break that further into subclasses of specific types. For example, an embankment is a type of flood defence. For each of those asset types, Your model could then contain different sort of attributes that apply to certain types of assets. Just as a physical scale model is a representation of how a physical thing fits together. This sort of model is a representation of how data and information fit together. By using metadata to classify our data and information according to some sort of model, we make them easy to use in the future. At the EA, there are a few types of data classification that we use to manage our flood defence assets. For example, AIMS Inventory is our internal classification system for asset management. We also use Uniclass, which is an industry-standard classification used by asset management organisations across the UK. It allows us to share information and data about assets and elements of assets across the industry. Finally, to build up cost estimates, we use classifications such as CESM or CESWI, which are industry-standard classifications for the cost of construction. Now you know some fundamentals about data, information and knowledge, let's talk about BIM. BIM stands for Building Information Modelling. What that means is that when we build something in the real world, we also build an information model in the digital world. The idea is that during the design and construction of our assets, we collect data and information in a structured way. If we have data and information stored in a manner that makes it easy for us to find again, then it will help us to apply our knowledge to better manage our assets. We can make better, more timely decisions based on accurate information. The principles of BIM are that we build a digital representation of the asset we build. As well as creating the physical asset in the ground, we build some sort of digital model of it which contains all the data and information we need to operate and maintain the asset. That we receive and store asset data and information in a structured way that relates somehow to the assets we've built. In other words, we make sure that information is received in a consistent way across all our projects, which enables us to find it easily later on. Create the single version of the truth. Everyone works from the same data, in a common data environment. This stops silo working and helps collaboration. This also builds trust in our systems and confidence in our data and information, which strengthens our knowledge. Consider the whole life of the asset we build. BIM is about changing the way we deal with information and data. Better information management. Think of it this way. At the moment, we receive files which have information and data buried in them somewhere. Our asset management teams use a data store which contains data and information about all the assets they operate. So when a new asset gets handed over, they need to make sure they collect the data and information for the new asset. In this scenario, someone needs to manually extract the asset data from the files and add it to the data store. This takes a lot of time. The end goal with BIM is to construct a model of the assets we build, which contains asset data. Then we can use this model and the data built into it to extract drawings, reports, and so on. In this situation, you can generate documents from the model, which means they get updated as the model gets changed. And more importantly for us, since the model contains asset data, when we want to hand over the finished asset, we can simply export the data from the model and automatically transfer it to the asset data store. This improves collaboration in the project team and makes it easier to hand over asset data and information to the operator when the project is complete. Terminology. In this section, we will introduce some key BIM terms and explain what they mean. In particular, we will look at level of definition, location and volumes, and how they are used to classify information, and how COBie is used to transfer data. Level of definition is a description of how well defined a model or piece of information needs to be. Throughout the life cycle of a project or asset, we don't always need very specific information. For example, early on in the project, you might not know what you're going to build. And you probably won't know the shape, size, or materials used in the construction. But by the time you get to the construction stage, you definitely need all these things to be defined. LOD is comprised of two components, level of information and level of detail. Level of information describes how specific the data or information behind the model needs to be. For example, at the concept stage, you might just know the type of defence you're going to create. Later on, though, you will know much more, such as the exact type of structure and the key features of its design. Level of detail relates to graphics and how well defined a graphic model needs to be. Sometimes, all you need is a line on a map to show you where an asset is. In other times, you'll have a full 3D model of the asset. The level of definition is defined as a number, which aligns to the stages used in the life cycle of an Environment Agency project. The LOD for a specific element is given as the level of definition you would typically expect at a certain stage, which gives LOD 0 to 6. When specifying information, you can ask for whatever LOD you want. It doesn't have to align to the stage definitions. For example, here is how a particular item might develop over the first few project stages. Let's say the team wants to bring forward work on this element of the project, perhaps to help with securing external funding or approval. They can do this by specifying it with a higher level of definition. This tells whoever is responsible for that item that they need to deliver it to a greater LOD. In this case, bringing forward the level of definition to LOD 4. Equivalent to detailed design. At stage EA3, the definition or business case stage. BIM introduces the concept of location codes. These codes are used to classify data and information according to the physical location of the thing they describe. For example, if you have a document that relates to a specific part of your scheme, you tag the drawing with the location code of that feature. The location codes are associated with coordinates which place them in the real world. Here's a map of the Tappenden Beck flood alleviation scheme, which protects the town of Beckford from flooding. Our document relates to the pumping station in the village, so we can show on the map exactly where that information relates to. We can do this the other way as well, which makes it very easy to find information later on. For example, if you want to find something about a certain asset, say the flood wall which protects Beckford from Tappenden Beck, all you need to do is search for its location code to find all the available information. Another concept introduced by BIM is that of a volume. These are similar to locations in that they're used to classify data and information, but they're a little bit trickier to describe. A volume is defined as a manageable spatial subdivision of a project based on an important aspect of the design. A simple way to think of it is this. If locations describe where something is, volumes describe what type of thing it is. Volumes are used for clash detection, to identify when different elements of a design run into each other, so they can't overlap in 3D space. Let's look at a couple of examples to try and make sense of this. This diagram is included in PAS 1192, the standard which defines key terms and procedures for BIM. It illustrates some example types of volumes that you might see on a project. As you can see, this is a cross-section through a train tunnel, and the volumes relate to the features inside the tunnel. In the EA, we have a standard list of volume codes which align to the types of asset we maintain. This table shows a subset of the volumes we use. Again, the volumes relate to the type of asset or feature. So, location define where something is, and volumes define what type of thing it is. Volumes and locations are defined in the volume and location strategy. This is defined by the information supplier whenever they are commissioned to carry out work. This process will be explained in Module 3 of the BIM eLearning. COBie stands for Construction, Object, Building Information Exchange. It is a standard format for exchanging data and information about built assets. One of the principles of BIM is that as we build an asset, we collect the data we'll need to operate and maintain it. If we're collecting asset data, then we need a way to exchange that data between teams, so that, for example, the team responsible for the design can pass the data they've created onto the EA's maintenance team. That's the idea of COBie. It's a format for exchanging information about built objects. What this means is that we can collect asset data, things like the crest level, standard of protection, cost, etc., as the project is carried out. With COBie, we don't need to interrogate drawings or reports to collect data. We can pull it directly from the model into a COBie file, which we can import into our asset management system. This saves time and makes the data more reliable. When you don't have models with asset data in this way, COBie also allows you to relate documents to assets in a structured manner. It allows us to receive information exchanges consisting of a COBie sheet, containing data, information, and details of file associations, with a set of documents, and then use the COBie sheet to verify the information we receive. During a construction project, we will receive a COBie data drop from the principal supplier at each stage gateway. The advantage of this is that we receive asset data during the project, as soon as it becomes available. We don't need to wait for the end to collect it all. That completes Module 1 of the Environment Agency BIM eLearning. In this module, you have learned some key concepts about data and information. You've learned the difference between data, information, and knowledge, about open and native file formats and when they are useful, how verification and validation are used to check that files or data are fit for purpose, that we can use metadata to classify data to make it easier for us to look things up. And you've learned what a model is and how it applies to information. You've also learned some of the key principles of BIM. That BIM is not just about 3D modelling. It's about collecting data and information to help us operate and maintain our assets. The levels of BIM maturity used to explain BIM adoption. That level of definition is used to specify how well developed a deliverable needs to be, in reference to the project stage. How to use volumes and locations to classify data and information. And the principles of COBie for data exchange. There will now be a short test of what you've learnt in this module. To pass, you need to score at least 70% overall. Good luck!